everyone. Today I'll be presenting a video entitled Exposing the Quantum Foundation of Relativity. So let's first of all go through what we hope to accomplish in this film. Well, it's a video. And in the end, we're going to go through the same list and just see if we actually achieved what we set out to do. So the first thing we want to do is determine the quantum explanation for an ordinary reflection of light from a mirror surface, such as is described by Richard Feynman in his book QED, which stands for Quantum Electrodynamics. Okay, so next we're going to derive the governing expression for ordinary reflection from this geometry. Now when I say ordinary reflection, I'm talking about you have a light, you have a mirror, and you have an observer, which for all intents and purposes could be your eye. And you've done this as kids. You're in your mother's bedroom and you look at the mirror and you see that at some point you see through the mirror and you see the what do you call a light? Anyway, what do you call a light? Oh, click, 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 you know. It's funny. The simplest of things. Click, 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 click. I don't know, bad light. So, ordinary reality is so much harder than this physics stuff. So, derive, next thing we want to do is derive the governing expression for ordinary reflection from this geometry. Then we want to solve for the location on the mirror where the quantum waves add to non-zero. In quantum mechanics, a lot of the phenomena are due to wave motion. Waves that are sort of, they don't really exist in terms of macroscopic measurements, like by our eye or by some meter, light meter, for example. They don't exist until it comes from a point where the sort of more intrinsic probability waves, some people call it that, although I think they're real waves in a medium, but they don't affect equipment unless they're at a point where the waves add. So, because otherwise they cancel out and you don't detect anything. So we're going to look for where those waves add, okay, in the reflection, and we'll find it. Okay, so last thing we want to do is show that this exact geometry also applies to the location of the observer. An observer in space traveling on his own timeline. Someone else, so some piece of equipment, might be a clock, it might be speeding away, traveling on another timeline. And we want to know for the observer on one timeline, looking over at the, let's say, clock on another timeline, what is the now? When the observer says that clock right now is boom. And you might have to calculate it using light waves, whatever. But when he makes that calculation, he draws a line, says, this is the line of the time when now, at this point, is now that time over there, right? So the line of now. So show that this exact geometry also applies to the location of the observer's line of now in relativity, and that the same principle of quantum superposition applies in determining the location of the observer line of now. So maybe many of you might be thinking right now, how the heck is he going to do that? It starts with a light reflecting off a mirror and ends up with the line of now. Anyway, that's why I made this presentation. I'm going to show you. And so here we go. This is my rendition of Einstein, Feinstein, Einstein. They always have Ein in it, like Ein means one, I guess. So they're number one. Feynman was number one in his field of electrodynamics, and I guess Einstein for a long time was number one in his field of general and special relativity. So Ein, this is Feynman's, my rendition of Feynman's setup here. And what we have is a light source at A, point A. Here, I'll use my red arrow. Point A, we got a light source. And at point D, we have a light detector, which could actually be a human's eye. It would work just as well as a human eye. Nothing special about it. except that everything in reality is very special, but nothing that we're not quite used to. For example, you got a lamp in your mother's bedroom, and you're over here, you're the detector looking at a mirror, and what you see is right through, it seems like you're looking right through the mirror along the line, let's say DC, along the line DC, and you look way into the mirror, and you see that lamp, and then you see that it's running straight along the line DC, but continues right into the mirror. That's what you see. But in physics, grade 12 or so, they show diagrams like this, and they're not talking about quantum mechanics. What the Newtonian explanation is that the light goes straight down here along the line AC, and it goes all the right to the line CA until it goes into the detector, and the light obeys the law called Schnell's law. It sounds like snails. Schnell's law, as if nature has is in a court, and there's a judge, and he's making everything follow these laws that were by these people's names. I mean, the whole way of describing it's kind of silly. At least I find it funny, and I laugh a bit. But let's keep our respect. Newton was a great. He did a lot of great work, actually, and we still use it in the low velocity, low mass approximation. Newton works very well. But yeah, anyway, there's no judge in court of law and all that I know of that makes this thing work. So back to this one. See these expressions on the bottom. What I want to do is, it's basically, we want to answer the question, what is ABD, which here's that, it's the purple direction. ABD to, ABD, that purple line there, that's a length, right? What's ABD minus ACD? Okay, ACD is A over here, C is over here at the center line actually. It's exactly the halfway between A and D, like Q is exactly halfway between A and D, so this C is on the center line. So ABD minus ACD, what is that? So let's just say again that QC is the center line, and this line PB is actually a measure of the deviation. So if when the line varies quite a bit, like let's say I'll use my red arrow here. If you're at point B and you go a little bit to the left on this diagram, and it changes its length dramatically, then it'll have a different phase. So when it comes down here and adds with B, for example, a light at point B, the phase is quite different. The phase is changing. And so when they add together, sometimes the waves are pointing up, sometimes they're pointing down, and they cancel out. So we want to see where are the, on this setup here, this experimental setup, where do the waves, quantum waves, superpose so that we can get an actual measurement? Like when we look down this line, we see light, the photons go in our eyes, and they're not canceled out. Now there's nothing in that vicinity to cancel out these waves, so you make a detection. And that explains why we think we see all the photons going from A to C to D when really they go everywhere. And Feynman's theory, which is shared by the majority, it's consensual now among a large branch of quantum mechanical theorists as well, that where the photons superpose and don't cancel is where we see them, where we can get a detection. Okay, so we say, well, what is ABD minus ACD? And I went and I worked it out. So ABD equals ABD, the blue total distance from A to D, following the blue line. ABD Um, and the square root tells you right away you're talking about a triangle. So where's the triangle? It's probably, what would it be? PBA is that triangle. And the distance and ABD, you need to get the diagonal. So they're going to take, I'm going to take the AB, or AD, divided by 2 is AQ, and then you get rid of BC right there. Get rid of BC, and you jump from Q to P, so that's AP, and then they say plus QC. Well, QC is the same as PB, so that gives you PB plus A squared plus AP squared, and that's going to give you the first half there, AB, okay? And then you still have to get from BD, it's going to be another triangle. So we do that here, and it's going to square root to get the diagonal. And like I said, I don't want to get into all this, you go to sleep. But that's all I'm doing, and if you ever are truly interested, you go through this, it's very, very simple. And then we want to know what is ACD, and I do something very simple, similar, looking at the triangle QCD, and just working out, Pythagoras, ordinary Pythagoras. So I've put it there. If I was you and you're really interested, in knowing the details here, I'd just print it out and go through and check. Oh yeah, I don't want to do that to you right at the moment. I've given you what you need to know. But what I did is I worked out that ABD minus ACD is equal to this. And I just basically took these two results above here, and I subtract them to get the distance. So ABD minus ACD. And I worked out that it's equal to this expression on the top here. Now I could have derived it analytically and spent a lot of time, and then if I showed you, that would probably really put you to sleep. But what I did is I just put this in an Excel chart and plotted it. And what I found is that when BC, this distance, deviation from the center line, when DC got close to 0 here, I will use my red arrow. When DC got close to 0, the slope is essentially flat. You can see this line here, this blue line, goes up. As the distance BC gets greater and greater, they start climbing up, like almost looks like an exponential kind of thing. But near the point where B is close to C, the slope is flat. So meaning the change in the total length is not significant. And what that means is that the phase of the different photons going that close to C, when they strike the mirror, they don't change phase very quickly with minor variations in distance. So when you sum all the waves, when you get far away from C, the slope is quite dramatic. So it gets higher and higher, the slope. And what that means is that the phase of the waves of the actual quantum waves are not photons until they're detected as photons. Those waves change phase very, very rapidly. They cycle, and when you add them, they add to 0. So you don't detect them there. So when you're very close to C, you detect photons, and you see them with your eye over here with a meter. But when they get away from C, any significant distance, they all cancel out. That's why when you look in the mirror, you see the light, the point that intersects the center of the mirror, and it explains Schnell's law. Okay, so remember, I plotted this, and I found that this is the curve talking about the distance difference. The distance difference of ABD, where the photons strike the mirror farther away from C, and ACD. And when B is close to C, the distance is very similar. The waves will still line up, and you'll see it. So a small distance around C, you're going to see the waves, quantum waves, add up, and you're going to be able to make a detection of photons, and that describes what you see. Okay, so that's for a mirror. Now, I'm thinking beyond a mirror. Like when I saw this, I thought, oh, this explains more than just a reflection on a mirror. And so here I'm going to strip this diagram here. See, notice I have A, B, the same setup, and same geometrical setup. And I'm going to simplify it even a bit more, because this is where what you really see. This I'm showing both BD, BC, and that as part of the diagram. Now I'm going to get rid of that. So I just show A, C, D, because that's basically, I mean, there could be a little wiggle around C, but that's kind of included in this diagram if you just blew it up. And this shows the place where the quantum waves add, okay, and where you can make a detection, right? So now, next chart here. I heard a lot of people, and I still see a lot of very respectable physicists say something that I find disturbing. They say that you can go backwards and forwards in space, but you can't, like time and space, they're not really the same. I mean, people like Minkowski and Einstein said that we live in a four-dimensional continuum, of space-time. There's no longer an independent time and an independent space. But physicists still today, they do all the math, and I'm sure they get the right answers. A lot of them are renowned physicists. But they say that, in spite of all that, we can go back and forward in space, but we can't do that in time. Well, I made a particular presentation. I gave you the link there. In addition to a bunch of others, I'm going to give you all the links at the end. But like I said, I made 9 presentations so far, and I've got a lot more to go. But now I'm in the sort of free zone. I've fulfilled any obligation I had to, respect Einstein and make sure I understand everything and that you understand everything. If you look at my stuff. And now we're at a point where let's get down to something that at least I've never found in Einstein's work, and I've never seen this in any other work either. So we've done our time, and let's now learn some new things, and maybe some people will dispute it, and I welcome that. It's nice to have people read things and say, I disagree with this, or I agree with that. And that's how science evolves. So here we are. I did this playful, but very extremely rigorous. I probably did more expressions that are true in this playful presentation entitled, and I have it right here. I'll get my handy wand there. Yeah, a gravitational time portal between Camana and La Riconada, Peru. And they're really, it turns out, it sounds so like, time portal. Well, that's science fiction. That's crazy. But the funny thing is, there really is a time portal between Camana and La Riconada, Peru. And if you really look at it, it's a friggin' time portal. And I describe how, in that situation, how people actually do go forward in time, and then go backwards in time. And it's when you look at the 1 second is 300 million meters or something like that. It's when you balance the units, let's say measure the whole thing as in meters would be a good approach. You find that the changes in time that you can experience at between Camana and La Riconada, they're long. When you put it in terms of the distance, the equivalent distance, these are long distances. I mean, when was the last time you walked to the moon and back, right? It's these kind of distances, and you say we can move back and forth in space. Well, great, go to the moon and back, right? I mean, so there really is a true deep equality between space and time, and we do just in exactly the way that we move back and forth in space when you apply it to time. And I show also in probably several places in the series of presentations that I'll show you at the end. I show that one observer's space is another observer's space and time. So you can, just like you convert mass into energy, you can convert time into space, and vice versa. So one observer's time is another observer's space plus time. And so space can be converted into time and vice versa. They really are, and when they are interchangeable, and they're really part of the same continuum. And space and time, they're basically depending, if your quantum waves, your momenta are moving in one direction, that is only for you, and everybody else is moving with you. That's your timeline, and that's your direction of time. But it depends more on how you're moving than some intrinsic characteristic of that proportion of space-time. No, it's all the same. I know people's minds spin, but anyway, so I do talk about that. Now, why am I saying this? I'm not just saying it to make people's brains hurt, although it's good to exercise your brain to the point where it kind of, you get that wobbly feeling every now and then. That's where your neurons are finding how to reconnect. It's actually, I think it's an essential part of scientific creativity. So what we're going to do here is I take the same diagram that Feynman was working with, where we established that the quantum waves add very close to this point C, and that there's, you notice here that the line of between Q, the observer, and C, where phenomena can be observed, it on this green line, the line QC intersects at a right angle. So that geometry, I want to preserve that, and preserve that right angle. This is one observer on here, Q, and another observer on C. Now, since time and space are convertible, and it means that they're intrinsically the same phenomena, just different ways of experiencing it from different observers. Will experience it different, but same phenomena. Same with time and space. And what I'm going to do is I'm going to, this diagram here is basically it's like a static diagram, although the light is moving, right? But the line AQD and ACD there, that okay, I'm going to get this one there. The A, C, D, and QC, those, we're going to rotate this diagram, and we're going to observe it from a different perspective. And this is a perspective where we have an observer traveling on the line AQD, okay? And the observer crosses the halfway point Q, okay? Now, you're probably thinking, what did he just do there? He rotated this geometry, which is laid out in space, and he took the dimension Q and C, and he pointed them in the direction of time. And yeah, that's what I did do. I rotated it because the orientation, there's no any specific orientation. Everything's relative, right? The orientation, and I can look at it from a different perspective, and I've taken the same geometry, and I've oriented it as somebody is traveling along the line AD, and that is their timeline. Then the momentum is going on the line AD, and likewise, someone's going on this green line, and that's their timeline, and there could be a clock moving on there. And you say, for this geometry where the lines are parallel, you say, at this point Q, what would the clock read now, right? And they say, well, what is the line of now? And where? Well, it's this line, this dotted blue line here that goes from Q to C. And that, for the observer at point Q rather, the only thing he can detect as and now is something going on at C, because that's the time for Q, observer Q. That is the time now over at C, okay? So this diagram expresses what people know and accept for relativity. Specifically, nothing's curving there, so this would be something to do with special relativity, but you can generalize it to general relativity very easily. And just as in this diagram, over here on the I guess it's the left-hand side of this chart, for the mirror with the two light source, the light source and detector, just thinking here. Yeah, so I lost that particular thought. It'll come back to me. The line of now over here. So for Q, oh yeah, I remember now what it was. The where this point C, where you see the waves superpose and can make a detection, depends on the where the quantum waves align. And since all I did is take this geometry where we showed that we proved that the place where the waves align, remember, because the slope goes to zero, the slope of change. In other words, they all have the same phase at that point, so all the waves align and superimpose, so you can actually take a detection along this line QC. Likewise here, it's the same geometry, and the quantum waves go through time as well as space. In this case, they're going through space and time, and over here, actually, they were going through space and time as well. So it's the same thing. The same thing applies. The only place where the quantum waves can add with respect to Q is at C. At C. So C is the line of now for the observer at Q. And it's purely a quantum mechanical effect. Now what's very, very interesting is people normally think about quantum mechanics, oh, that only applies to small little objects like electrons and protons and this sort of thing. Well, this line of now can apply to, you can put spaceships in there, you can put rockets in there, you can put, well, that's the same thing. You can put mountains in there, you can put a planet. Well, it's not going to be a dot though, but a little tiny, heavy planet, you know, a dwarf star or something. Put it there. And it's quantum mechanics that determines for the observer riding along the red line there, and it comes to point Q, what is the time over there, the line of now, what is now over there where the dwarf star is, and it's the line QC, determined by quantum mechanics. So quantum mechanical phenomena really at the heart of even macroscopic phenomena and of gravity. And right there, what that shows is that the foundation, and I want to say one other thing I've said before, but the line QC intersects always, when you're talking about an observer observing someone else, like this point C, okay, and it could be an observer, it could be a piece of equipment, observing as well. But the line of now is determined by where the quantum mechanical waves add, okay, they superimpose to a non-zero, and that always will be at where you put the right angle between QC. The right angle goes on the observer line that you're observing, not the observed line. So earlier on, in probably other presentations, I said you have to put the right angle over on the line that's being observed, not the observer line. And I was going to explain it later why you have to put the right angle there. Well, it's because we're reproducing this geometry here where the right angle is here, and it's the line QC intersects at the line green line with a right angle here by necessity, and that establishes the place where the quantum waves add rather than canceling out. Because if you go away from QC or away from C enough, which is the phase will rotate and rotate and rotate because the distance changes dramatically with little small perturbations. So, which it doesn't rotate and change much at the point C. It's got some sort of resistance to that, which we showed earlier when I plotted that line. I'll go back to that. What the heck? Okay, that line here, where I plotted how the distance varies how the slope, how the rate of change varies and increases as you move B away from C progressively. The slope, the rate of change of the phase of the quantum waves increases. So the waves are canceling out, and they sum to zero, or effectively zero. You don't get to make a measurement there. And that nothing can exist now at that point away from C. But at C, the waves add up. You can make a measurement and you say, oh, whatever it is, that clock is there now. I know because I measured it there. All right, so I think you're probably getting a feeling on this. And this is not necessarily the most obvious to a lot of people. I mean, it's quite a phenomenon. So, if your head spins a bit, that's good. And, sleep on it, maybe watch this again or something. But to me, it just pops out and I say, yeah, it has to be that way. So here I say, once you determine that there are undulations in the vacuum, then, I'll put an N in there. Then the geometry of space-time and the rest of relativity fall, I'll get rid of this, then, can I edit? Yeah, there we go. Fall into place as a natural consequence of these undulations. So some people call them probability waves. Once you determine that there are probability waves in the vacuum, then the geometry of space-time and the rest of relativity fall into place as a natural consequence of the, let's say, behavior of these undulations, where they cancel. So here we have it. When you're an observer traveling on the timeline here, and you're at point Q, you look over and take measurements, and you find that you're now over there at C is along the line QC. That's the distance line, the spatial line between point Q and C. And I say here over that, oh, yeah, okay. Yeah. This is the only place where the amplitudes of the waves from the perspective of Q, and the observer at Q, it could be a machine or a person, add rather than cancel. So we've gone through that before. It always corresponds to the right angle in the location shown. So you must always have a right angle here. When you're an observer looking at some equipment, it could be a clock or it could be a person, moving along this timeline, the green one, then the now is going to be that line that makes a right angle connection to the line, the green line. So Q will absorb C now as being along the distance line QC. Now, if you angled the timeline of the green one, for example, then that right angle would angle the line QC, and it can go up or down. And I covered that in great detail. I think it was in presentation 1 or presentation 2, general relativity 2, I think it was. Well, I went through and really analyzed well the twin paradox. A lot of people, they give answers to the twin paradox that really don't explain it. I mean, the worst thing for a human being is to get an explanation that doesn't explain something. So you think you understand it because it kind of, sticks in your head, and you go, oh yeah, but it doesn't really explain it. So I really do explain all of it, and it's really quite shocking, because in that, I'm going to digress just for a second, but in that I show that depending on how you move, you can you have a lot of momentum at your disposal to like as a rocket, where you can blast a rate of change of momentum and change your angle. And when you apply momentum, you don't change the actual velocity of everything's going at the speed of c, but you can change the angle by exchanging momentum with something. And it could be a rocket throwing matter out the back, at high velocity, and you get a rate of change of momentum when doing that. But you can change depending which way. Maybe the rocket has two rockets going both directions. So you go one way, and you go forward in time with respect to the observer, let's say on the timeline, and you blast the rocket the other way, and you go backwards in time when you look to the other observer. So you can. It's an interesting phenomena. But I did that in general relativity number 2. But in this case, you can see the lines are going straight, and there's no momentum exchanges going on, and so it's a static determination of. Although these guys are traveling in the timeline, so it would always be parallel, parallel, parallel as it goes up in the direction of the motion of the momentum in each of these reference frames, So anyway, that's that. I hope I explained it well enough for you. So now let's do a little bit of a wrap up, as I promised I would. So again, this presentation was exposing the quantum foundation of reality, and I just wanted to get into it and show that it really must be this way. And so I promised that, I'll get my red arrow. I promised that I would determine the quantum explanation for ordinary reflection of light from a mirror surface such as described by Richard Feynman in his book QED. And I actually went a little bit deeper than Richard did and showed the actual expressions and derived it. So I think I did that, and I really liked Richard's work. I think he was, in his own way, more charming and clear. And maybe I went a little bit deeper in some respects. And the use that I put it to is definitely, I would say, deeper and perhaps more controversial at this time. I don't actually know. I haven't seen anybody ever do it. So, okay. I lost my little arrow. It went in there, little bugger. I know what to do is I'll just send this back. Range, center back. Now I should be able to, yeah, okay, great. So the next part was derive the governing expression for ordinary reflection from this geometry. Remember I showed you how we did it. It was just Pythagoras. I didn't do every last one because it gets too boring, but if you want to see it, I actually did it. And then I plotted it, right? And it says, show that this exact geometry also applies to the location of the observer line of now in relativity, and that the same principle of quantum superposition applies to determining the location of the observer line of now. And for, when the observer is looking at a particular other timeline, that could be a clock, and the observer says, well, what is the now over there? Like, what time on that face applies to this moment right now, like this instant second, not even this fraction, this time right now. What's now over there? Well, that you draw a line over to the other timeline and make sure it interacts at a right angle, and that point over there on that line, at that where the right angle, the line of now intersects at a right angle over there, always at the right angle over there. That's the line of now for the observer on the other side. So show that this exact geometry also applies to the location of the observer line of now in relativity, and that the same principle of quantum superposition applies in determining the location of the observer line of now. So it's pretty essential to special relativity and general relativity to have the operating definition of the space-time geometry, and a large portion of that is knowing where is now for this observer, where is now over there. And you need to have quantum mechanics for to do that. Like a lot of people say, oh, well, what do you do? A lot of physicists, it's easy, just bounce a light over there, bounce it off the guy, and you come back. So the light went out, and then it came back, and you just take the time that it took for the trip out and back and divide by 2, and that was your moment now on you can say at this time on my clock it was now over there at the point where it reflected off of that mirror. That exact instant it reflected was that time. But you go back to Feynman, you say, hey, the way that the light behaved when it reflected, that's totally a quantum mechanical function, and it's totally dependent, what you see, on where the quantum waves superpose. So it doesn't help. It proves my point. So it's really powerful, and I think I can't see. Well, I don't want to say that, but because if you can't see some way out of it, maybe it's your mind that's the problem. But it seems very compelling to me. Let me just say that. So let's go to the next chart, where I promised that I'd send you my URLs for the presentations 1 through 9, and here it's number 7 there. A gravitational time portal between Cumana and La Rinconada, Peru. It's playful, but it's true. There is a bloody time portal there, and I describe how you can use it to go very large distances when you take the second and express it in meters, put them on the same platform footing. You can go out and back in time. Like I say, did you ever how many times you walked to the moon and back? I mean, in human terms, it's the same. You can go back and forward in time, and here's the caveat: you got to do it exactly the way that you do it going out and back in space. And I define that in this presentation of gravitational time portal, and number 7 there. And with that, you know what? I think we've done it here. So I'm going to tell you how much I enjoyed making this presentation. And with that, I bid you well and a good night.